about atomic theory. So what would you guess atomic theory might mean?
Periodic table.
Yeah, it might have something to do with the periodic table. It might have something to do with atoms, right? All of those are correct. So our topic for this chapter is really going to be learning about what makes up an atom. And we're going to learn a little bit about the periodic table, learn to apply some different trends on the periodic table, learn some rules about the periodic table, all that kind of stuff. But give me a little rundown of what we know so far about the periodic table. What do we already know about the periodic table? Way back to the beginning here. All right, we're going to go all the way back to early atomic theory. So we're going to work through different stages of atomic theory. What did they originally think about it? And then what do we think about it now? What do we think about it today? Okay, so early atomic theory started with a guy named Democritus. Have you heard that name before? No. Democritus thought that atoms were tiny particles that can't be broken down any further or can't be cut down any further, right? We agreed with that up until really pretty recently when we split the atom, right? When we were able to break the atom into even farther pieces. But his theory of the atom was that just like a little ball, right? And we can break it down until we get to an individual atom and then no more. And today we know that there are smaller parts of an atom, right? There's a proton, neutron, and an electron found within an atom. So we know that there's some smaller things that are found inside of that. Okay, the next kind of guy who had major theories about the atom was a guy named John Dalton. His atomic theory was based on experimental findings. So Democritus put together an idea of basically understood ideas, right? His first atomic theory from Democritus was like almost just like ideas of what's possible, right? Here's what we think we know. And then John Dalton put together all sorts of different experiments and put his findings together to publish his first atomic theory. So those were the first kind of two major atomic theorists. Aristotle also had a big theory on atoms, and his was that matter in itself really was only 5 different types of matter, right? There wasn't a lot of different elements, that there was 5 different types of matter, and all of that made up everything. And so we knew that was kind of dismissed. We're going to walk through now, we already talked just a little bit about how atoms are made up of protons, neutrons, and electrons. And I'm going to walk us through kind of how did we get to that information, okay? We're going to start with the discovery of the electron, okay? A guy by the name of J.J. Thomson did an experiment early on about metals. And his findings through this experiment were that no matter what type of metal he worked with, there was always a negative charge being given off. Okay, there was always a negative charge. And he always found out that there was the same amount of negative charge being given off, regardless of the different types of metals he worked with. And so this led him to an understanding of this negatively charged particle. He called this particle an electron. Okay, so we need to understand that electrons have what type of a charge? Negative. They have a negative charge. Okay, electrons have a negative charge. You will see me abbreviate electrons like this. If we're talking about electrons or writing it out, you'll see me abbreviate it like that. Why do you think I abbreviate it like that? What's that little thing mean? It's just indicating that it's a negative charge. So an E with a little minus sign like that, I'm going to abbreviate. That means electrons. Okay, so when I say it has 14 E like that, it's going to mean it has 14 electrons. Okay, that's what that means when I say that. Okay, so Thomson gave us the first, the first real prominent picture of what the atom looks like. Right, this was one of the early atom models, right, atomic models, and his Thomson model was basically just like this. He said atoms are circular. And they've got an even distribution of pluses and minuses found within them, right? He knew there was electrons or negative charges. And so there's got to be something positive that's balancing those out to make them neutral. So he said they're just spread out evenly throughout the atom. Okay, that's not what we know today about the atom, but this was the Thomson model. So this was an early and pretty prominent model of the atom. Okay? His research was with metals specifically, but he was able to tell that just because it was present in metals, they had to be present in all different elements. So his research led him to believe that there's got to be electrons in every type of element. So he kind of was able to expand that out of just the metals he tested. All right, so now let's talk about the discovery of a couple other parts of the atom, okay? Next is going to be the nucleus. The nucleus, okay? A scientist by the name of Ernest Rutherford discovered the nucleus. And his experiment that he did is really, really famous. It's called the gold foil experiment, okay? Rutherford's experiment is called the gold foil experiment, okay? So I'm going to kind of walk you through what was the overall point of that experiment and what it concluded with, because it's kind of interesting, okay? What Ernest Rutherford did is when he took these particles called alpha particles, and alpha particles are positively charged. That's the most important part of that. Alpha particles are positively charged, and they're heavier than a hydrogen atom. So they are positively charged, and they're heavier than a hydrogen atom. And he took this source of alpha particles, and he tried to basically shoot them through a gold foil sheet. Okay? His expectation was that the alpha particles would just fly right through that gold sheet, right? Knowing what they knew about the atom at that time was that an atom was just a circular sphere with positives and negatives sprinkled all throughout, right? That's what they knew about the atom at this time. And so his expectation was these positively charged particles won't really have any effect, right? They're just going to go right through the foil. And so this is kind of what he expected to happen, right? Here's the Thomson model, the red one, and he expected his positive charges to just go right through, right? To have no problem. But what actually happened is that here is his alpha particles right here on the bottom, right? They are being sent through the gold foil, and a lot of them do go right through. But what happened to these ones here?
Deflected?
Yeah, they were deflected. They were redirected the minute they hit that gold foil. And so I want you to think about this. What would a positively charged thing have to hit in order to be deflected? Yeah. No? Okay, so what would happen between a positive and a negative? They would connect. And so what would it have to hit? It has to hit a positively charged thing. Think about when you put like two wrong ends of a magnet together. Will they go together? No, right? They're going to repel each other. And so that's what's happening here. We've got a positively charged particle hitting something else that's positively charged and causing it to deflect or causing it to repel. And so that's what he found in this experiment. And so here's some of the kind of discoveries or the conclusions he drew from the experiment, okay? Some of the particles did pass right through, and some of them were changed directions. And so his conclusion from this experiment, right, if you have a positive hitting another positive, he said there's got to be some small positively charged region at the middle of the atom that's causing his alpha particles to redirect. Okay, and he called it the nucleus. Okay, he called this region at the center of the atom the nucleus. Okay, the nucleus has to have a positive charge because it caused those alpha particles to deflect or to redirect. Okay, and then his suggestion, since they already knew based on Thomson's research that atoms are made up with electrons. So he's got to come up with a system of where are the electrons at then, right? And so his decision on it was that the electrons were orbiting the nucleus, similar to the way that planets orbit the sun, right? That's kind of what he envisioned for this, is that electrons were orbiting the nucleus. So unlike the Thomson model had the electrons spread evenly throughout the atom. His model, the Rutherford model, has the electrons orbiting the nucleus and kind of sitting around the outside. So his conclusion was that most of the atom is really made up of empty space. So I'm going to show you what that model looks like, and you have that printed on the next slide there. That next atomic model is called the Rutherford model, okay? Or some people even call it the planetary model. Why do you think it might be called the planetary model? Yeah, it looks like it, right? That one looks like planets orbiting the sun, right? Or something like that. So it's called the Rutherford model or the planetary model. So, yep. in the planetary model, if he says the electrons are orbiting the nucleus, that would mean that we've got an electron on one electron on each of these lines. One electron there, one electron in that orbit, one electron in that orbit. So if I only have one electron in each of these orbits, how much of my atom is empty space? A lot, right? A lot of my atom is empty space. I've only got one electron present. That means all of the rest of this is empty space. What's in here? This is the nucleus. The whole thing is the atom. This is the nucleus. What did we say has to be in the nucleus?
Neutron and proton.
It's got to be positive. Okay, it's got to be positive. And so we know that those are going to be protons. Okay, so here's a couple other things that he decided. He decided since our atoms are neutral, there's got to be some positive charges to offset the negative, and he called those protons, right? Our alpha particle ran into something positive. They've got to offset the electrons that Thomson discovered, and so he called them protons. All right, he also decided that since electrons have such a small amount of mass, right? Electrons are really, really, really tiny, even in comparison to protons. That there's got to be some other particle that accounts for some of the mass of the atom. It doesn't change the charge, but it changes the mass. Do you know what particle that is? The neutron, right? So we call those neutrons. Neutrons have no charge at all. Okay, so you might see me abbreviate protons with like this, P with a plus, right? Because protons have what charge? Positive. And then you might see me see neutrons with a little zero up on this side because neutrons have no charge at all. They do not have a charge at all. Okay, so he said that neutrons account for the mass of the atom or some of the mass of the atom, but not the charge. Okay?
Wait, can you go back?
Yes.
How did you write this?
Right? Because normally a positive and a neutral would not pull together, right? They would not attract. And so there's a special type of force that holds them together called a nuclear force. Okay? I want to give you just a really brief example here, and this number might not even be exact, but I want to say, like, if a proton weighs 1 AMU, my guess would that an electron would weigh like 0.0001 AMU, right? It might even be one more degree smaller than that. I can't remember off the top of my head, but an electron has a mass that is so small in comparison to protons that we don't count it in the mass of the atom, right? The electron has a mass of a really, really, really small amount, right? So we just ignore that when we're counting up the mass of the atom, right? Because protons and neutrons contribute to the mass, but electrons do not. And it's because they are so much smaller than protons are. Okay, so in the nucleus, we know we only have protons and neutrons because electrons are in the outer parts of the atom. Okay. Oh, I was close. About 1,800 electrons. So I was one place off. But an AMU is equal to about 1,800 electrons. So the mass of the electron is ignored when we find the mass of the atom. I apologize. I put up the wrong number there when we did it the first time. But it's really small. All right, here are some things that we know about atomic theory today, right? We know that matter is composed of small particles called atoms. Atoms of one element differ in properties than that of another element. Okay, so atoms of different elements behave differently. Atoms of the same element always have the same number of protons, but they might vary in their mass. All right, so I've got all 5 of those points up there. And then I want to walk through a couple of those here in just a second. 5 points here. Okay, it says atoms of one element differ in properties than that of another element. So atoms of hydrogen do not look, act, behave the same way atoms of oxygen do, right? Hydrogen and oxygen atoms behave differently. Hydrogen and carbon atoms behave differently. Atoms of the same element always have the same number of protons, right? That's really important. The number of protons is the single identifying characteristic of an element. So if I ask you for what element has 19 protons, you're going to tell me always it's potassium, right? And that's really what we're going to focus on next class. But it always has the same number of protons. They might have different masses, which means they might have different numbers of neutrons. Atoms of different elements have different average masses, and atoms cannot be broken into smaller particles in ordinary chemical reactions. So those are all parts of what we know about the atom today. Some of them are still very clear with what John Dalton wrote, and some of them are a little bit new. Okay, and then there's your definition of the atom down below.